Hello, Professor.
How are we doing tonight?
Tired.
Excuse me. Oh, I hear you. Just had some tea go down the wrong way. So where are we? Are we halfway done?
Like with the semester?
Yeah.
I don't know. We just turned in homework 10, so is it the 10th week right now?
Well, see, tonight is, why do I have the wrong lecture up for tonight? No, that's the right lecture. Combined loading.
And Professor, the next homework will be on November 10th, right? So we don't have any homework for next week.
That's right. That's absolutely right. Combined moments and action. No, this is the right one. I just have the wrong. Wow. Today's the 29th. I got the 27th on here. Okay, well, maybe it'll fix itself and maybe it won't. Anyway, yeah, I guess I was going to say, don't we have 15 weeks, right? So 15 weeks would be more or less 30 lectures minus a couple midterms. So I don't know, are we like 2/3 of the way? Maybe.
We covered.
Yeah, lecture 20. Okay, well, I got this called the right thing. I just got the wrong date on it. Okay, anyway. Never mind, it's lecture 20. Never mind, that was last Tuesday. But we are going to talk about combined loading for tonight. Before we do, let's do a little checkup. I'm going to bring up another file here. Syllabus. Okay, can everybody see the syllabus?
Yes.
Awesome. Yeah. Okay, so we are actually on track, believe it or not. Today's the 29th, and tonight is combined loading. And then I have a lecture on thin-walled pressure vessels. That is supposed to be the next one. And then, of course, a week from today is the big night for our midterm number 2. Make sure everybody has a working webcam for that. And we will start promptly at 5:30. Do not be late. Or unless, you know, you're super confident and you can take the test in less time, that's okay, I guess. But I would suggest not to be late. And then after the midterm, we have 1, 2, 3, 4, 5. We have this little holiday in there, 6, 7 more lectures after that. And then we have our final on the first week of December. So yes, the next homework assignment, you might have noticed, homework 11 is not due on the 3rd. I thought I'd give you guys a break so you can study for the second midterm. So the 11th homework is due on the 10th. So a little less than a week and a half away. And then after 11, we have 12, we have 13, and that is it for homework. Again, you have another week off, yay, yay, so that you can study for your final exam. And that's how this is shaping up to be. Any questions about the schedule or where we're at? Okay, and then let's do tonight. Tonight we talk about combined. Yes, David. Final will be cumulative. Tonight we talk about combined loading, where we are going to combine moments. What we talked about last lecture, we talked about having biaxial bending, where you can have bending moments about the x-axis and or you can have bending moments about the y-axis. Well, now we're going to combine it all, no pun intended. We're going to combine it all to add an axial loading to moments that could be about the x or the y-axis. So as I said, we have both bending stresses and axial stresses are normal stresses. Okay, so bending stresses, my over I creates a normal stress. Bending moments, bending moments, my over I create normal stresses. Axial loads cause normal stresses as well. So that means that bending stresses and axial stresses can be added directly by superposition. Okay, so let's reiterate what a positive sign convention looks like. This is my positive x-axis. This is my positive y-axis. We talked about this last time when we introduced the flexural formula. And remember what I said, why is the x-axis off to the left? The answer is because I said it is. That's why. It has to be. Or else positive moments won't cause compression in the top of the beam like they should. So if I look at an isometric view of my positive x-axis, my positive y-axis, looks like so. So now we're going to add to our bending moments, we're going to add axial load. Okay, so if you have a load that is going down, then P is less than 0. P is a negative load that's going down and it's compressing the member. So if the P is less than 0, that is compression. And as you can see, this block is being compressed by this load going down into it. If P is greater than 0, then as you can see, it is tending to pull the member apart, and that would be putting tension into there. So the sign convention is important when you start using the equations. You need to be sure that you have the right positives and negatives where they belong. So we can have an axial load at some eccentricity. Eccentricity, E sub y, in this case, is an eccentricity in the y-axis, the y direction. And an axial load at an eccentricity creates a bending moment. So we can replace an axial load at some eccentricity with an axial load that is located right at the centroid. And we have to add in a moment about the x-axis, m sub x. So m sub x is equal to the axial load P times the eccentricity in the y direction. Okay, so this is a direct result of superposition. And this is saying that this condition here, forgot to get my little shiny star, here we go. So this axial load with this eccentricity is equivalent to an axial load going right down the middle of the beam plus an added moment. And this is the way we're going to look at things. If you have this condition, you need to convert it to this condition so that we can solve it for your stresses. Likewise, we can have an axial load that is located with some eccentricity to the y-axis, which is an eccentricity in the x direction. So this would be E sub x is an eccentricity in the x direction, and it is creating a moment about the y-axis. So I can take my point load, my axial load, and I can relocate it on the centroid of the beam as long as I add a moment to compensate for that, that moment my equal to P times E sub x, okay? So you can have an eccentricity in the y direction, you can have an eccentricity in the x direction. You can have an eccentricity really in any direction, as long as you bring that resultant back to the 0, 0 point at the intersection of your coordinate grid, the centroid of your beam, and add the appropriate moments. E is a measure of how far off from the centroid that load is. It's inches. It's a distance. Does that answer your question?
Yes, thank you.
Okay. All right, so if we pull it all together, axial loads create a stress. Remember, we're going way back to week number 2 or 3. Axial loads create a stress equal to P over A. We kind of started with that. And then we have our flexural equation here, minus mxy over I, plus, when we make it a biaxial equation, myx over iy. So this is the total. When we first introduced P over A, that was just kind of a fraction of it. When we first introduced my over I, that was a fraction of it. This is the most general form of the equation that accounts for axial load, moments about the x, moments about the y. Any questions about this? Okay. Again, P, if P is pointing down, then it is going to be less than 0. It is in compression. If P is pointing up, P is going greater than 0, and it will be representing tension. Mx and My are both equal to P times the appropriate E about each axis. And the sign of E, okay, the sign of P is determined by whether it's in compression or tension. The sign of P is whether that load is up or down. The sign of E, the eccentricity, is it positive or is it negative, follows your axes. So if it's in the same direction as the positive Y, then it's a positive number. If it's in the opposite direction, it's a negative number. The combination of the two ought to produce moments that follow the right-hand rule for your sign convention. And as I said, X and Y are distance from the centroid to the point of interest, which may or may not be the same as E. X and Y are positive or negative as determined from the sign convention of the axis. Oh, okay, so these X and Y's are the distance from the centroid to the point of interest. That's this guy and this guy. Not to be confused with E. E is in the mx and the my. So E is the eccentricity of the load. X and Y are the distance from the centroid to the point of interest. Like if I say, what is the stress at the upper right corner? Well, then X and Y are the distances from the centroid to the upper right corner. That's not the same thing as the eccentricity of the load, okay? So I think maybe some examples might help. Okay, so if this is our section, the good old 2x4, and this is my loading. So my loading is 10 kips located on the y-axis. So the eccentricity in the x direction is 0, but the eccentricity in the y direction is 1.5 inches. So if this is our situation, what are the stresses at this corner A and this corner B? So first step, P is pointing down. P is tending to put this element into compression. It is compressing down on it. So we must take P to be minus 10 kips. Again, I cannot reiterate enough how important it is to keep these sign conventions straight. Okay, so if I take my P and I relocate it to the centroid, then I must add a moment to compensate for that effect. And that moment is equal to P times the eccentricity in Y. From the diagram and from the right-hand rule, mx is determined to be positive as drawn. Okay, so if I take my thumb along the x-axis and I curl my fingers in the direction that this load would tend to rotate, then I get a positive mx. So mx is equal to 10 times 1.5 inches, which is 15 kip inches. Okay, so let's slow down for a moment and really kind of analyze this. It would be confusing, I think, to say right here, I said P is equal to -10. So why didn't I do -10 times positive 1.5 inches? The 1.5 inches is in the positive Y direction. The 10 I just said is -10. So how come the moment's not -15 kip inches? Are you guys confused about that? Is this clear? Am I making it worse? What do you
No.
think?
Well, is it the right-hand rule?
So what I'm saying is the final definitive answer on these moments is the right-hand rule. So if you look at this load, don't think of it as positive or negative for the moment. You just see that it's pushing down. And pushing down would tend to rotate this way. So I draw my moment in the direction that it would tend to rotate, right? I'm replacing this eccentricity with this moment. And then I put my thumb on the x-axis, curl my fingers. Is it in the same direction as that moment? Yes, it is. So that means it's positive. So this is a positive 15 kip inch moment. Okay, is everybody good with this?
And in this way, we have to follow the sign convention, which is x, positive x pointing to the left and the y, positive y to the up, right? We don't have.
Absolutely right. Yes, it only works. What you just said is absolutely right. It only works if you draw the y going up and the x going to the left, and then you get the right moments. So, but yes, that's exactly what I'm trying to say. You can visually see where the load is. If this load had been pulling up instead of pushing down, then you would have drawn this the other way, because you can see pulling up would try to rotate clockwise about the x-axis. So you would have drawn the moment the opposite way. Then you would have put your thumb on the x-axis, curled your fingers and went, oh, that's the opposite. So that would have made it a -15 kip inch moment. And we're going to do exactly the same operation about the y-axis as well. Just in this case, there is 0 moment about the y-axis because there was no eccentricity of the load about the y-axis.
Professor,
Yes.
if the 10 kips was closer to B, would that change anything or no?
Sure it would. If the 10 kips was over here, right? Okay, so that's a good question. So what if the 10 kips was actually here, pushing down here? Then what would that change over here?
It would be a negative moment.
It would be a negative moment. This load would tend to spin the element about the x-axis in a kind of clockwise direction. You know, if the clock is on this face, it would be a clockwise rotation. So that means that you would have to draw this going this way. And then you put your thumb on the axis, curl your fingers, and realize that this moment is the opposite. So that would have made it a minus 15. So this point load located off of A produced a positive moment. The same load off of B would have produced a negative moment. That answer your question, Adriel?
That was my question, but yeah.
Oh, I'm sorry. Okay.
Professor,
Yes.
if there's also, in addition to the load P going axially, if there's also a moment applied at this cross section of the beam,
Yes.
would, after you relocate P to the centroid and add the moment that it causes, would you then add this moment to the other applied moment before you continue?
Yes, you would.
Okay.
Yes. Yes, that's exactly what you would do. You would add all the moments about the X into one resultant moment. You would add all the moments about the Y into one resultant moment. And then you could even have multiple axial loads for that matter, but you would find the resultant of all the axial loads and put them right at the centroid. Because the equation that we're going to be using, the P over A only ever works if the P is right in the centroid of the A. Okay, I'll say it again. The P over A to find axial stress, the P over A only ever works if the P is located at the centroid of A. If it isn't, you have to find the resultant that is and add these moments.
Okay, thank you.
I have a question.
Yes,
So,
please.
Professor, the distance E is always positive, and
No, E is not always positive.
how is it become negative then?
Okay, so if, again, if the point load is over here, then the distance to E, okay, let me think about that for a minute. So, no, you're right the first time. E is
Yeah.
always positive.
Because if you're just like looking at the point and then you're basing P for the moment, then E will always be positive, right?
That's kind of
Because
tricky. Yeah,
because I was thinking earlier that it becomes positive because the E is negative 1.5, but you explained it. It's the moment. So I was like, oh, so E is always positive then.
right. So let me do this. And I'm really trying hard to not make this more confusing. But if the point load is right there, then E technically is minus 1.5 inches because it's in the opposite direction as the Y. So you'd go down here and you'd have 10 times minus 1.5 is minus 15 kip inches. And it would produce a moment going this way. So you use your right-hand rule, and that would confirm that it's minus 15 kip inches. Or I suppose you could say, all right, E is always positive. So this is 10 times 1.5, that's 15. But then I'm looking at the right-hand rule, and this says it's negative. So I'm just going to put negative in front of the 15.
Yeah. Okay.
You see what I'm saying?
Mhm.
So I think it's mathematically correct that the E is actually negative if it's in the opposite direction as the axis, but you can always confirm that or even determine that by using the right-hand rule.
But for, let's say the P was on the x-axis and it was to the right of the Y, then technically E would be negative, but it would still create a positive moment about the y-axis.
Okay, that may be true. Let's see. It's over there, right?
Yeah.
Okay, so that produces a moment going this way. And the right-hand rule would say that that is positive.
But E would be negative according to the X convention.
That's right. Yeah,
So it's probably easier just to think of E as always positive and then just look at what type of moment is creating and then compare it to the right-hand rule.
I agree with that. I think that's the safest bet. Yep.
All right. Thank you.
Okay, so I think what we're agreeing on is that basically draw it the way that it is, figure out what direction the moment has to be in order to get the result into the centroid, and then use the right-hand rule to determine if that moment is positive or negative. Okay. And we'll go through some more examples. You'll kind of see how it shakes out. Okay, so the sign determined from summing moments with the right-hand rule. So that's kind of what I had on the presentation too. All right, in the Y direction, what I'm showing is that I still have a 10 kip load, but the eccentricity, the distance from the Y-axis, is exactly 0 inches. So I have 0 moment about the Y-axis. Load is located on the Y-axis, so eccentricity from the Y-axis is equal to 0. Okay, so using my general equation for normal stress, using the flexural formula, I can now start plugging in some numbers. The area of my 2x4 is 8 inches squared. The moment of inertia, we're kind of got this memorized by now, 10.67 inches to the fourth. Iy is 2.67 inches to the fourth. At point A, now here's where it becomes very critical. E was the distance to the load, and we're saying use the right-hand rule to determine if that moment's positive or negative. But X and Y rigorously follow the axis conventions, okay? So the A corner is this back corner over here. In the direction of Y, it is a positive 2 inches. In the direction of X, it is a minus 1 inch because it's opposite of the axis. So this is followed rigorously. Is really the only way to get the proper X and Y values to plug into here and here to get your normal stresses. Okay, so I'm now plugging in sigma A, the normal stress at A, is P over A. So there's where I'm saying that's where your minus 10 kicks in because it's putting it in compression. So minus 10 over 8 inches squared minus my positive 15 kip inch times a positive 2 inches over 10.67 plus my 0 moment on the Y. This is irrelevant at this point, but minus 1 inch is the X over 2.67. And I get a normal stress at A of minus 4.062 KSI in compression. Compression because it is negative. At point B is the opposite corner. So there, my Y is going away from the positive Y axis. So I have minus 2. X is still minus 1. And so I go through the same equation. But now instead of 2, I have minus 2 for Y, minus 1 for X. Everything else is the same. And I get 1.562 KSI in tension. So if I draw an isometric of my stresses are constant in the X direction because I have no moments about the Y. That's the moments about the Y is what would skew it. So at A, I have this negative, I'm in compression, and at B, I have a positive, I'm in tension. your neutral axis is that purple line right there where you have zero stress. Okay, any questions about example 1?
When you're looking for the X and Y, like you said, at point A and B, X is -1 because it's in the back corner, right?
Yes, positive X is to the left, and from the center, A and B were both 1 inch in the opposite direction.
Okay, thank you.
Okay, everybody ready for example 2?
I have a question, Professor.
Sure.
So you said that's corner A and corner B, right?
Corner A is here,
Yeah.
corner B is here.
So it will be the same answer in the other side? of the
Yeah,
line?
it would. Yeah. If I called this C and I called this D, you can see right here that the only thing that would change for corner C and D is this term
Positive.
and this term would both be +1, but these were both multiplied by 0, so it wouldn't change.
Oh, okay.
Okay, and so that's why I'm saying that the -4 and the +1.5 is constant because there's no moments about the y-axis.
Right. Okay. Thank you.
Okay. Okay, I'm going to bring up a concept called the kern. And the kern is, it deals with the idea of, actually, let me go back here one. Okay, as I mentioned, see this purple line right there? That's where you have 0 stress, 0 tension, 0 compression, just 0 stress. So here's a concept of a kern where if you keep the axial load within a certain distance, then you will never have tension in the member. If the load gets too far, then you will have tension. But if I keep the load in enough, then I do not have tension. So back to this example, the load was applied at 1.5 inches and I got this much tension. Well, if it wasn't 1.5 inches, but something less than 1.5, then I could design this to have no tension. So the kern is, where is that magic line? Where's that magic boundary where as long as I stay inside of that boundary, I have 0 tension? Okay, so that's what we're going to be looking at. The reason? Some materials just don't tolerate tensile stresses very well at all. So we need a way to determine where they keep the load so that stresses are always 0 or on the compression side. Okay, so if I look at a plan view, this is my positive x-axis, my positive y-axis. I have my width b, my height of h, and we're trying to find this magic eccentricity that is right at the boundary of no tensile stress. So if I look at my flexural equation, and at the moment, I'm not looking at moments about the y-axis. I just want to find it. See, it's located on the y-axis. I just want to find my boundaries in the y direction with my moments about the x-axis. So I set my y moment term to 0. And I set the whole equation equal to 0. I want to find where's that magic eccentricity that produces exactly 0 stress. Okay, so then I come down here and I made some substitutions. The area is equal to the base times the height. The moment is equal to P times E, and it's E that I'm looking for. Y is H over 2, and I sub X is BH cubed over 12. Okay, so everybody agree with my substitutions? Anybody not agree with my substitutions?
looks good.
Okay, great. I still set the whole thing equal to 0. Okay, so now I can make some simplifications. You notice that P washes out. The magnitude of the axial load doesn't matter. And so, and B washed out. P and B both wash out. So I'm left with H over 2, H to the third over 12 equal to 0. And now I can start making some simplifications. I add this over here, and then I just solve for E, and E is equal to H over 6. That's the magic boundary. So this is the concept of the kern. If I go up in the y direction, H over 6, and I go down the y direction, H over 6, and then of course, if you flip the whole problem around and solve for it in the x direction, you'll get the same result. You get this diamond shape. And the full length of the diamond in the y direction is H over 3, H over 6 plus H over 6. And the width of the diamond in the x direction is B over 3, which is B over 6 plus B over 6. So what this is saying is that if you have an axial load that is producing compression, an axial load pushing straight down, but it's located somewhere inside this diamond, then you're guaranteed to not have any tensile stress on this member. Mustafa, do you still have a question or?
No, I'm fine. Thank you.
Okay. All right. So this is kind of an important concept if you are trying to not have tension in your construction. So as long as the compressive load is located in the kern, no tension will occur across that section. Okay, so here's a real world example of why or how would this ever be important. Everybody's familiar with Gothic cathedrals. Gothic cathedrals used flying buttresses to resolve thrust forces from high arches. Okay, so in case you're not familiar, this is a typical flying buttress situation supporting a Gothic church. And it's basically supporting the vaulted roof on top of this thing. The inside of the church, you had these fairly thick walls, and you have this really heavy roof up here because everything's made out of stone. So the weight of this roof is producing a thrust that is pushing outwards on these walls. And before they came up with the idea of flying buttresses, they just had to make these walls really, really thick out of stone. And that was kind of depressing because you couldn't have a whole lot of light coming through here because the walls were so thick. So to make these much more elegant and beautiful, they could thin the walls tremendously by putting in these flying buttresses to resolve that thrusting load. So the weight of the vaulted roof creates a load down the bearing walls and a thrust. Because Gothic churches are constructed of cut stone only, did you guys know this? There was no cement or mortar, so they cannot resist tensile stresses. All the Gothic churches of 1100 to 1300 AD were just really, really fancy, elegant piles of rock. There's no cement, there's nothing holding those things together except for massive, massive gravity weight just pushing down on them. So without mortar, without cement, and certainly without rebar or some kind of a steel, they can't resist tensile stresses. Therefore, the pilaster under the flying buttress must be heavy enough to keep the resultant axial load within the kern. So here's this thin wall that has the big, large stained glass windows in it. this is the thrust from the mass of the roof above, and the thrust comes down the flying buttress, and it goes into this pilaster. Well, this produces an overturning moment on this pilaster. But as long as the moment and the weight keeps that resultant within the kern, then you have no tension. Oops, that was my last slide. So that's a real world example of keeping stuff in the kern. What happens if this thrust produces a moment large enough that it's outside of the kern? How do you resolve that, so to speak? Anybody? How do you get that load back into the kern?
Increase the width or the base. Increase the dimensions of the what's it called, cross section.
Yes, you can increase the dimensions of the cross section to make the kern bigger. And what you can do is increase the weight on this, because the weight of it, remember, it's P times E. So the more weight you have on there, the less eccentricity you're going to have on it as well. So you have all these fancy adornments and, you know, all those gargoyles you see on Notre Dame. Well, those are structural gargoyles. They're there for a reason to add the weight to keep that thrust down. Okay. So any questions on the concept of the kern? Any of you guys, oh, dare I say this, any of you guys old enough to have watched The Simpsons? Do we have any Simpsons fans?
Yeah.
Okay. So this is probably, I know they're probably, what are they on, year 30, 35, something like that? But way back when, I have no idea, season 4, season 5, I don't remember when it was, but it was The Simpsons, and it started to show off with the hurricane, and a hurricane came through Springfield and wiped out everybody. So everybody pulled together and rebuilt the Simpsons house. Anybody remember this one? Okay, nobody remembers this one. Well, you know what? It's on Disney Plus, isn't it? You can go back and find it. Well, there's a scene in there where Bart Simpson goes up to his room and there's a poster of Krusty the Clown. And I forgot if it was Bart or somebody else, but I said, I don't like Krusty the Clown. And they ripped the poster off. He goes, no, you can't do that. That was a load-bearing poster. Maybe it was the Flanders' house. Maybe you're right. Maybe Flanders. Yeah. But it was a load-bearing poster. So that was the one show that us goober structural engineers really appreciated. So that's what I mean by a load-bearing poster. That's a structural gargoyle, you know. All right, moving on. Example number 2. We are going to look at a steel C-clamp used to clamp 2 objects together. If a compressive force of 50 pounds is screwed into the clamp, so you expand these 2 screws until you exert a force of 50 pounds, then what is the maximum tensile and compressive stresses in this section up here? That's what we want to set out to find out. So if the body of the clamp is 1/4 inch wide and 3/4 inches deep, then we want to know what is the stress at the top and bottom of this section of the clamp. So taking a free body diagram, here's half of the clamp, and we're going to have this 50 pounds is compressive, it's pushing into the screw, and we have a moment and we have a nominal axial load at the section that we are concerned about. The eccentricity of the load is 3 inches for this C-clamp here. So we sum our forces equal to 0, and we have 50 minus N equals 0. So 50 is positive, 50 pounds, and it is in tension. Our moments, we sum our moments equal to 0. We have 50 pounds times 3 inches minus M equal to 0. Our moment is 150 foot or pound inches, which doesn't sound like a lot, does it? 50 pounds of tension, 150 pound inch of moment. So the area of my section is 1/4 by 3/4, 0.1875 inches squared. My moment of inertia is 1/4 times 0.75 inches to the third over 12 that's really, really small, 0.0879 inches to the fourth. So if
Wait,
yes.
Sorry, can you go back just real quick?
Sure, sure.
Okay, thank you.
Okay. So now this is that section. I'm looking at it on end. I have my positive X, my positive Y. I have the top and the bottom that I want to find my stresses in. And the whole section was 3/4 high. So from the neutral axis or the centroid to A or B is 3/8 of an inch. So I use my flexural equation. I have 50 pounds in tension, so the 50 is positive. P over A minus my positive moment, 150, times Y is 3/8 of an inch over 0.0879. And I had 0 moment across the Y. So I have minus 6133 PSI in compression at A. And at B, oops, that's not kips, that's 50 pounds. And minus the 150, but now Y is negative at B because it's the opposite direction as the Y axis. So this is where you got to be rigorous in the application of X and Y. And this produces 6,666 PSI in tension. So that's how we resolve those forces. Any questions on example 2? Okay, example number 3. Given the following geometry and loading, find the normal stress at the corners of A, B, C, and D. So there's our friend, the 2x4. Only this time, my load has a Y eccentricity and an X eccentricity. So you can see how this is going to play out. I have to relocate the load to the centroid. And using the right-hand rule, I have a positive X moment, and I also have a positive Y moment. So MX is PEY and MY is PEX. From the diagram and right-hand rule, both MX and MY are determined to be positive as I've drawn them. So MX is 10 times 1.5, 15 kip inch. MY is 10 times 0.75 here. So that's 7.5 kip inch. So now I can lay into my flexural equation. My area, kind of, like I said, we have these memorized by now, but 8, 10.67, 2.67. So at point A, and I redrew this in plan view so you can kind of see where A, B, C, and D are located. At point A, Y is equal to 2. I went up 2, and I went over -1. So I plug in P over A. This is compression. It's going down. So that's -10 over 8 minus my 15. 15 was positive. 2 is positive, plus my 7.5. 7.5 is positive, x is negative, and I get minus 6.871 KSI negative, so it's in compression. Once you have written this out for one corner, then it's super simple, especially if you're using like Excel or something, to set it up for all the rest of the points. Because the rest of the points, the only thing that changes is x and y. So at point B, now I'm down 2, and I'm still negative 1 over. So minus 2, minus 1, and I plug them here and here, and I get minus 1.247 KSI in compression. Point C, y is minus 2, x is positive 1. And this becomes very repetitive, but minus 2, positive 1, and I have 4.371 KSI tension. Last point D, positive 2 up, positive 1 over, and I plug these into here, minus 1.253 KSI in compression. So I want you guys to see that the point of interest is A, B, C, or D. And the point of interest determines X or Y. But it does not change this negative. It does not change positive or negative of the applied moment. The applied moments were found by the right-hand rule. So that doesn't change. The axial load in the area doesn't change, and certainly the section properties, moments of inertia, don't change. So once you've written this out for one corner, the only thing that's going to change from any other location of interest is the coordinates of x and y. So now I can draw this out in a three-dimensional. And these are all the corners drawn to scale. Positive is in tension, and B, A, and D were all in compression, negative. So this is actually like a solid shape, and the purple line again is the neutral axis. Mustafa, about finding the average, we plugged the stress P over A. Which average are you looking for?
So in this method, we're just finding like the stress in the specific points.
Yes.
And the average, if we like want to find the stress, the average stress, we have to plug just P over A, right? Such as in units in chapter 1 and 2, I think.
Good question. I think it would be. I think it would be the average stress. Now, technically, to get the average stress, what you'd have to do is take the volume of this shape and divide it by the area of this. But a sneaky suspicion that might work. 4.371. Minus 1.247 minus 6.871 divided by 4. I do believe that's true. Okay, so I took the average of the four corners and I got P over A. P over A is minus 1.25. Minus 10 over 8 is minus 1.25. I took the average of the four corners. Right there. So I averaged A, B, C, and D, and I got P over A. So yes, Mustafa, I think you're correct. Okay, you guys ready for example number 4? This one is an interesting one. So what I have created for you is some sort of a steel fixture welded to an embed plate that is fixed to a wall, and it has a tube steel welded to the wide flange, with a cap plate, and we're putting these loads in here at the top of this tube steel. So we have the loads as noted, and we have these eccentricities from the center of gravity of the steel beam of 24 inches and 36 inches. And this is my local coordinate system, X, Y, and Z. Okay, so everybody see the problem statement? So what we're gonna ask for is find the normal stress at A, B, C is at the centroid, E and D, D and E, of course. So the dimensions that we need here is 2.015 is from the y-axis to the corner there, and 3.14 is from the centroid to the top or to the bottom there. Even though that looks a little funky, it's meant to be from there. So the beams, these are real beams. This is a W6 by 16, pulled it right out of the steel manual. And these are the section properties, as you can see. So Y bar is 3.14. That's this distance from the center to the bottom or from the center to the top. X bar is from the edges to the center. Moment of inertia about the X, moment of inertia about the Y. So we're going to need these section properties to determine the stresses at these points. First step, always the first step, find your reactions. So I'm going to sum my forces in the X direction. X is in this direction here. So I have what were the inertias? These, 32.1, 4.43.
Sorry about that. I just missed it.
Okay, no problem.
So how many reactions we have? 3?
Well, good question. You tell me, how many reactions do we have?
Should be, I don't know, 3 or 2 at the moment.
How many degrees of restraint do we have in a three-dimensional problem?
Is it
At
a
a
6 degrees of restraint, right?
6. We have 6 degrees of restraint. We have forces, excuse me, we have reaction forces in the X, Y, and Z direction. That's 3. We also have rotational fixity about the X, about the Y, and about the Z. So that's 3 more. 3 forces and 3 rotations that are all fixed at point C on this diagram. So you have 6 unknowns to restrain this, right? Okay, so if we start by summing our forces, the first one we're going to look at is our reaction. I'm calling this, this whole end is A. So my reaction at A minus the 4 kips is in the X direction. So I have a 4 kip reaction, and I'm kind of drawing this in my isometric direction this way. Sum the forces in the Y. I have my reaction at A plus 30 kips up. So my reaction at A is minus 30 or down. And I have my reaction at Z is equal to 0. I have my reaction at A plus 10 kips. This guy here is located along the Z axis. So I have minus 10 kips. My reaction is in the opposite direction. Sum the moments about X. Okay, so this is my X. So I have a restraining moment about X. I have 10 kips with a 24-inch eccentricity trying to rotate about X. And I have 30 kips with a 36-inch eccentricity also trying to rotate, but in the opposite direction about X. So I sum them all together. The 4 kips doesn't play into this because the 4 kips is collinear, parallel with X. There is no eccentricity about X for the 4 kips. So that drops out. I sum this up and I have a 840 kip inch reaction about the X. I do the same for the Y. About Y is anything trying to twirl this thing about, about the Y. So I have 4 times 36. The 10 kips, it has 0 eccentricity, and the 30 kips is collinear, so it has 0 eccentricity. So only the 4 kips times the 36-inch eccentricity. So my moment about Y is a minus 144 kip inches. Yes, I do. I'll show you the directions in just a sec, but absolutely, you need the directions. And then lastly, moments about Z. So that's about this axis here. And the 4 kips has a 24-inch eccentricity. The 10 kips is collinear. The 30 kips has 0 eccentricity, so only the 4 kips counts. And that gives me 96 kip inch. And here are my directions. So I had about the Y, you do the right-hand rule, and about Y, this is negative. About X, this is negative. About Z, this is positive. So these are my end reactions over here. Any questions so far? Okay. So this is a view of my end. My X, Y, and Z are at my reaction here at the end, and I've drawn in all of my reactions. The beam is experiencing equal and opposite forces. So what the beam is experiencing is the opposite, 840 in the positive direction, 10 kips in tension, and 140 in the positive Y direction. You notice I am not showing you the force in the X, and I'm not showing you the force in the Y, and I'm not showing you the moment about Z. Why? Why did I leave those 3 off?
Because they are on the axis.
Close. Anybody else? What did the 3 things that I left off all have in common? And I'll say it again, a force located along X, a force located along the Y, and basically a torsion about Z. What do those all have in common? All 3 of those produce shearing stresses. And I'm not interested in shearing stresses for this problem. I just want the normal stresses at A, B, C, D, and E. So I'm only showing you the 3 reactions that produce normal stresses. The axial load, the moment about X, the moment about Y. That's why. So Vx, Vy, Mz omitted as these produce only shearing stresses. According to the right-hand rule, both Mx and My are positive. Mx is 840 kip inch, My is 144 kip inch, and the axial load was tension. Okay, so now we can start using our flexural formula at point A. Y is positive 3.14 because I'm going up to get to point A. X is 2.015 inches, positive because I'm moving to the left to get to A. My load was tensile, so that's 10 kips tension, minus positive moment, positive Y, plus positive moment, positive X, and that gives me minus 14.56 KSI in compression. Once you've set it up correctly for one point, the rest of the points fall in really easy. So for point B, I am up 3.14, but I am in the opposite direction to get to B as the positive X, so that's minus 2. and I plug positive, negative, I get minus 145.56 KSI in compression at B. At point C, Y is equal to 0. Point C is right at the centroid. X is equal to 0. So therefore, at point C, I have 10 kips over P over A minus my moment times 0 plus my moment times 0. And I have 2.11 KSI in tension at the centroid. At point D, now I go down 3 inches and I go positive over 2 inches, plug and chug. I get 149.78 KSI in tension. At point E, I am down 3.14. I am over minus 2. And so plug and chug there, and I get 18.78 KSI in tension. So these are my normal stresses at each one of these locations. That's the last part of this example. Do I have any questions?
For the reaction that you says, or
Uh-huh.
is that the A over here in your diagram?
Not exactly. Okay, so the A in this diagram is just locating this,
That corner, right?
that corner. And then let's go back up. There's a number of slides, but let's go back up. Okay, so little a is just that corner right there. But I think what you're asking is here, when I said reaction
the
at A,
RX, yeah.
that was just meant to be this whole end.
Oh, okay.
So I was just finding the reactions at this fixed end. So this is, I apologize, that's kind of a bad choice, but this, I could have made this capital A and made that capital A and capital B over here. But once we had all of the forces at this end of the beam, which is here, then I designated each one of these little locations within the beam like a local reference point to be little a, b, c, d, and e.
Oh, okay. That makes sense.
Okay, yeah, sorry, I could have used a capital A or something else to make that clearer. And also, I did kind of do, because I wasn't really focused on finding the internal forces of this beam, but this equal and opposite, you could prove this by the longer way to do this problem, and I would have totally ran out of time, but the longer way to do this problem is to, once you found your reactions here, which is this and these forces, then you would take a cut through here. And once you take that cut, then you would sum up your internal forces, your internal moment about Y, internal moment about X, and the axial force. And then once you found those internal forces, those are the forces you plug into your flexural equation. I took a shortcut. Instead of making that cut, I basically just said, because there's no other forces applied along the length of this beam, that everything is equal and opposite for the internal forces. Okay, so does that make sense? In order to focus on the flexural equation, I really took a very shortcut of just saying that the internal was equal and opposite. But the long way, the rigorous way, the proper way to do it would be to make a cut and sum your forces about that cut.
So did you flip the signs for the forces and the moments?
Did I what? I'm sorry?
Did you flip the signs?
Yes.
Okay.
Yes. Yeah, I found my reaction here. So I said my internal load is here.
So could we use this method like in the exam?
Oh, I wouldn't do it. Oh, I wouldn't do that. No, 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 no. change one little thing and this doesn't apply. So again, I'm not saying this is how you should do it. I'm just saying that I picked a very complicated problem to show you the complexity of this step. And to get to this step before 8 o'clock tonight, I took that shortcut. I would not recommend you do this on an exam.
So it's gonna be another story if there's like a moment applied in the beam. Like you cannot do what you did. Like
If you had any loading applied within the body of this
Yeah.
beam, then yeah, then it doesn't apply because you gotta take your cut points and figure out what's going on internally within there.
okay.
Yeah.
That makes
Again, I took a shortcut to get to the meat of the problem to show you what I wanted to show you. I do not recommend you taking that shortcut on any kind of exam problem. I would not expect you to. I would write the problem so that there's sufficient time for those who have sufficiently studied to do it the proper way. Any other questions? I mean, we have 3 whole minutes. So, I mean, we can really get going on this. So A and B are in compression because of the internal moment, correct? And then C and D are in tension for the same reasons. Yes and no, Nicholas. I think you're really close. Remember this 10 kip load right here. You can still see my screen. This 10 kip load would tend to put the whole section in tension. But these two loads here are really cranking in a large bending moment this way and this way. So at the corner of B, both this moment and this moment are ganging up together on the corner at B and really cranking in a lot of compression. For the same reason that corner D, they're both ganging up and creating a lot of tension. And then this 10 kips over the whole section isn't really adding a whole lot to that, but it's in general putting the whole section into a little bit of tension. Does that make sense, Nick?
Yeah, thank you.
Okay, great. Any other questions?
Professor, could you go to slide 111?
Slide 111?
Yes.
How did you know what slide 111 is?
Oh, because I have it open over here. I think there's a typo when we talk about the stress on B.
Probably. Okay, let's. Come on, baby. Can't. Okay, hold on. I'll get there with 1 minute to spare. Okay, slide 111. This slide?
Yeah, so you have the same exact formula, but different answer.
No, they're not exactly the same.
What is the difference?
Right there and right there. This is positive because
Okay.
it's at A. This is negative because it's at B.
All right, I see. Thank you.
For once I didn't have a typo. I feel so good about myself. Okay, just kidding. Any other questions?
For the midterm, would we be tested from, I think it's like lecture 10 till lecture 19 then, or just today?
Were you here last lecture?
I was a little bit late.
Oh, okay. Actually, yeah, we're kind of out of time. I would go back and review that because we talked about it. And we will talk about it again on Tuesday because the midterm is on Thursday. But I already covered that last lecture and we'll talk about it again on Tuesday. Is that okay?
Yeah, that works. Thank you. I just wanted to confirm the start date. But if you said in the other video, that works. Thank you so much.
Okay, no problem. All right, everybody, have a great weekend, and we will see you next week.